Hello, welcome to Math 1960. Today we are going to discuss alternating series um, and absolute conversion. So we would be able to determine whether an alternating series converges. We would be able to approximate the sum of conversion alternating series, and we would also be able to use the absolute conversion test. In this So an alternating series is any series that its term changes sign. So here this is positive ace of 1, this is negative ace of 2. This is positive ace of 3, this is negative ace of 4. And then similarly, there is an alternating series that start with negative. So here negative ace of 1, positive ace of 2. Negative ace of 3, positive ace of 3, where all k's greater than 0 are greater, a's of k are all greater than 0. The numbers a's of k where a's of k here greater than 0 of an alternating series summation from k equal to 1 to up to infinity of negative 1 raised to the power of k plus 1 a's of k, or an alternating series where k equal to 1 up to infinity of negative 1 raised to the power of k a's of k. So in order for this series to converge, limit of a's of n has to be equal to 0. Terms of a's of k are non-increasing. That means a's of 1 is greater than or equal to ace of 2, is greater than or equal to ace of 3, and so forth. So in example number 1, we want to determine whether this series converges. So the first test is we want to find the limit of ace of n. So we find limit as n goes to 0 of 1 over n. This is equal to 0. And then now we want to find, so here 1 is greater than half, half is greater than 1/3, 1/3 is greater than 1/4. So the second test is also satisfied. That means the series converges. So in example number 2, we want to determine that this series converges. So first of all, we take the limit as n goes to infinity of 2n squared plus 9 over n squared plus 1. That should be equals to 2. The limit of that is equal to 2. And if this limit is equal to 2, that means 2 is not equal to 0. So the first condition is not satisfied. That means the series diverges. So in example number 3, this is an alternating series. So first thing, to find whether it converges, we want to find the limit of ace of n, which is at this point is going to be 2n factorial. This is equal to 0. So, and then now we want to examine. So the first condition is satisfied. We want to, for sure, 2n factorial would always be greater than 1 over 2n plus 1 factorial. Here I'm dividing by a big number, all right? Okay, and here I'm dividing by a smaller number. So this clearly is greater than this. So so since two conditions are satisfied, that means the series converges. So for error conversion of alternating series, so if we sum up, usually what we do is to sum up some terms of the alternating series, and these terms call them S of n, right? So summation, we sum up n terms, and then we approximate this n term to be the sum of the overall series. Doing so, we usually have an error, and that error is usually equals to E of n is less than or equal to S of n plus 1. So in this table here, so if I sum three terms, right, and then if I sum those three terms, and then I say, well, the summation of the overall series is equal to the summation of that three terms. So the summation of three terms is that the error from there is 0.24. And then if I approximate the summation using 9 terms, that error is 0.1. If I approximate the summation of the overall series using 99 terms, the error is 0.01. And if I consider 999, so the error would be 0.01. So the more terms I consider, the less the error. So here we want to approximate the sum S of the alternating series so that the error is less than or equals to this. So my biggest task here is to find when, so I know that E of n is greater than or equals to S of n plus 1. So I'm trying to find that S of n plus 1, where error is equal to it or less than it. Okay, so I'm going to consider different terms. So here S of 1 is equal to 1, S of 2 0.5, S of 3 is equal to 0.0416, S of 4 is equal to 0.1388, and then S of 5 it's going to be equals to this is here double zero here, double zero point, S of 5 is equal to 0.00004 times 25. This is clearly, this S of 5 is clearly less than or equal to this, right? So that means I'm going to sum up these 5 terms to give me the sum so that my error is less than this. So that means I'm going to say A1 minus A2 plus A3 minus A4, and that should give me 0.540. That is the summation, okay, of the overall series, given that my error is 0.001. So now we will discuss the absolute and conditional conversion. What is the absolute conversion? Well, the absolute conversion, if I have a series like this, I want to find the absolute conversion of it. I'm going to say absolute value of S of 1, absolute values of S of 2, absolute value of S of 3. We find that it's conversion. If series S of k is absolutely conversion, then it is conversion. Use the absolute conversion test, determine whether the series is converges. So right now we are going to find the absolute values of each and every one of these. If I then my series would looks like this. summation from k equals to 1 all the way to infinity. So here I have 1 over 2 raised to power k minus 1. So when I substitute for k for 1 here, I'm going to get 1. When I substitute here for 2, I'm going to get negative 1/2. Then here I'm going to have the alternating series k plus 1. Okay, so and then this is going to give me like this thing here. So that means right now this ace of n I have r is equal to 1/2. This is geometric series. It converges because it's geometric series. Okay, so use the absolute conversion and determine whether this series converges or not. So first, we are going to take absolute value of each one of them and then sum them up. So here we may say ace of n, it's equals to sine n over n squared. This is always going to be less than or equals to 1 over n squared. Because sine n, absolute value of sine n is less than or equal to 1. When we divide by n squared, so we divide, so first we may say sine n is less than or equals to 1, and then when we divide by n squared both sides, okay, so that means now if this one here converges, that this also must converge. So then I'm going to take the limit of that, and then this apparently this converges. This is equal to 0, so the whole thing converges. The whole series converges. That's it.